So let's very quickly recap what we saw. So we are talking about MOSFETs. We went through all this. So let me skip to that really fast. Okay, so let me go back here. So the first thing to keep in mind, this is the structure we're looking at for a P-type device. So very briefly, again, the three terminals here, so the transistor. The control terminal, perhaps the most important terminal, is the gate. The input terminal is the drain. And the input voltage, the input terminal is the voltage across the drain and the source. And the output is typically the current from the drain to the source. Okay? So we have a device which looks like this. You have a P-type substrate. You have an N+ region on this side. So you have a drain, N+ to P. This is reverse biased, typically, this PN junction. As is this PN junction is also reverse biased in normal operation. Okay? So what happens is that when you apply a positive voltage to the gate, you push the holes away and you attract electrons to the small region near the interface. And you create an electron channel. Okay? Once you have the electron channel, then when you apply a voltage between this and this terminal, current will flow. Okay? So by controlling the gate voltage, you can control the electron channel there. So that allows you to control how much current flows. Okay, that's a qualitative picture. Quantitatively, of course, there are two things that happen. One is you can switch it on and off. So if the channel is not present, it's off, the current doesn't flow. If the channel is present, it's on, the current flows. So that's on and off. Now to do amplification, we know that the gate voltage relates to the channel conductivity non-linearly because of the depletion width. Okay? We model that. Look at that very quickly. So any signal you apply to the gate translates to the current with some amplification. Okay? That's the amplification factor is called transconductance or conductance. Transconductance if it is a differential amplification. Okay? dI over dV. Okay, so that's the main picture here. So far, that's what we know. Okay, we looked at the math approximately. Now, last class we talked about capacitance, but the capacitance we're talking about is in this direction. So keep that picture in mind. It's a little bit confusing. The current is, of course, flowing from left to right. Okay, the capacitance that we have been talking about, and we will talk about today, is the gate oxide capacitance, which means that recall that no current can flow here, right? This is an insulator. But this is a capacitance. And we showed that this is more or less like a parallel plate capacitance. Okay, you have a metal here, you have a dielectric oxide here, and then you have a pseudo-conductor, right? You have an inversion layer and all that. So it's a little more complicated than a parallel plate capacitance, but that's the capacitance that we're thinking about here. Now, that capacitance is important because when you do amplification, the signal goes on the gate. Right? So the RC time constant when you apply an AC, the signal there, is the capacitance here, not here. Okay, that's the input capacitance. So we need to know that. We need to understand how it varies. Okay, and that's what we'll focus on today. The current voltage characteristics is a little bit different. It will be in this direction. Right? That's just like the FET. Okay, that's what we saw before, very similar to that. So let's talk about the capacitance quickly. So we did the qualitative analysis. I'll skip that. Oh, the other important thing, of course, is that we have a pinch-off situation here as well. And the idea is that as you increase the gate voltage, at some point here, the depletion region starts encroaching into the inversion region. So this light blue region is the inversion channel. Inversion because it has become N-type from P-type. So it is inverted its sign. Okay, its type. But you also have this gray region, which is the depletion region. As you increase that voltage, it becomes more, as you increase the drain voltage, this junction becomes more and more reverse biased. Okay, so this depletion region will get bigger and bigger and will encroach into the inversion region as shown here, and that's what causes pinch-off and saturation. So it's a little bit different mechanism than the FET, where it was just the depletion region cutting off the channel, right? Similar idea, but slightly different physics. The other important thing, of course, is that we have a threshold voltage, which means that there is a minimum voltage that needs to be applied to the gate before an inversion layer can be formed. Okay? So the transistor doesn't operate for a while until you reach some threshold. That's a very important parameter for MOSFET. And typically the threshold voltage is shown as VT, and that's a saturation condition. We know that the drain voltage greater than VG minus VT means is that condition right there, where the depletion region pinches off the inversion region. Okay, so those are two things to keep in mind. So we have a linear regime, which is over here, which basically acts as a resistor, and then we have the saturation regime. This is just at saturation, this is beyond saturation. Okay. And the principle is the same as FET. So make sure you keep this qualitative picture in mind as you muddle through the math, because otherwise it won't make much sense. Okay, so next, yes, we talked about the Metal-Oxide-Semiconductor Interface, which is the capacitance I was talking about. And we saw the band diagrams, which I won't go through again in the interest of time. And we calculated how the bands bend. Okay, so that you should know how to do this, by the way. Make sure you follow this. And we looked at how the charge density. Okay, this is sort of where we stop. So let me just briefly go through this. So we can treat the metal oxide semiconductor as a capacitor. Like I said, the signal, so this is looking at it, you rotate it 90 degrees from the previous picture. So we have a gate here, oxide here, semiconductor here. The signal comes here. Okay? So the impedance seen by the signal is whatever capacitance is here. So it's important to know that. So remember, when you have a circuit, you're going to put the gate will be the input to some small signal. So you need to know what impedance that signal will see in order to design the circuit. Okay, so that's the goal here. Keep that picture in mind. And later on, we'll put this into a circuit so you have some experience. So we know in this situation, when a voltage is applied, a positive voltage is applied, we know the inversion happens. And we know the inversion can be represented in the energy diagram by the bands bending such that the intrinsic level goes below the Fermi level, right? So it becomes N-type right at that interface. It's P-type far away. So that's inversion. Okay? So you have depletion happening in between, and you have an inversion layer. Okay, and you have the voltage gets shared between. Some of it gets dropped across the oxide. Some of it gets dropped across because of the bending in the semiconductor. So it's an allocation of voltage. Okay, that's straightforward. And the allocation of voltage is shown here, where this is the total voltage. Some of the voltage comes across the insulator, Vi, okay, and some of the voltage comes across phi s, which is the surface bending of the bands. Okay, we talked about that last time. So that's phi s, and that's Vi. This is a straight line, because in the ideal case, the insulator cannot have any charges. Okay, so the potential is constant. Across some distance, the electric field has to be a straight line. The electric field is constant, so the potential has to be a straight line. Okay, the slope is fixed. Now here, there is, of course, some complicated function which describes this bending, which is what we calculated before by solving the differential equation. Okay. Now, if you look at the charge density, in the ideal case, there are no charges within the insulator. Oxide cannot contain any charges, ideal oxide. At the interface here in the metal, you have some charge accumulation, positive charges accumulate at the interface of the metal. And on the other side, in the semiconductor, of course, we have an inversion channel. So remember that the electron current flow is out of the plane of the screen. Okay, so now we're looking at a cross-section of the MOSFET to some extent, right? Then we have a depletion region here, which is basically fixed ions, the acceptor ions in this case, in the P-type material. Okay, and the whole thing has to cancel out, so this should be equal to this in terms of charges. The whole thing has to be neutral. But from here, we can figure out the electric field and the potential. Okay, the drop across the insulator is essentially given by that. D is the thickness of the oxide. Epsilon is the permittivity of the insulator. And QS is the surface charges, which is inversion charge in this case. Okay, all of that's pretty straightforward. And you can define essentially an oxide capacitance per unit area. And we will see this becomes an important factor in transistor design for circuits. Okay, and this is something that device designers actually tune very, very carefully. And we'll talk about that also. Okay, so this thing, keep in mind. Okay, that's the oxide capacitance per unit area. Okay, now we can mathematically relate the oxide capacitance to the applied voltage. So first of all, first thing we should expect is that the capacitance will be voltage dependent, right? Because if you think about it, the charges here on this side are clearly voltage dependent, right? If I apply more voltage, I can make it more inverted, so I can create more charges here, right? If I apply more drain voltage, I can increase the depletion width, so I have more charges there. So clearly the capacitance, or the capacity to store charge, will be voltage dependent. So it's not a simple parallel plate capacitor, but this is like a PN junction, right? The PN junction had the same issue. We had a voltage dependent capacitance. So same kind of situation here. Now, to understand voltage dependence, it's very straightforward. First, we can relate the depletion width to the surface potential. Okay, this is just like a PN junction, the exact same equation as a PN junction, except that now we replace the bias voltage, V minus V naught, the bias minus the contact potential, with just the surface potential, which is just the bending, how much the bands have bent from the bulk. Okay, so it's logical. So after strong inversion occurs, the depletion width doesn't really increase much more with respect to the gate. Okay, which means that strong inversion means that the band here has bent down far enough, as far as it is up here. So this is as much p-type as it is n-type far away. That's the definition of strong inversion. Okay, so once we have that condition in place, then we have a maximum depletion width. Beyond that, really, it doesn't increase much, and you can calculate that based on this expression, where phi s is the onset of strong inversion, which we know because it's 2 times the difference between the intrinsic level and the Fermi level. Okay, so that's much p-type versus n-type. So you can relate easily to the concentrations of the acceptors, the p-type doping, and you get a simple expression like that. And that allows you to calculate the charge density in the depletion region, QD. You get, this is, again, common sense. This is the number of acceptor ions, which electronic charge, times the width of the depletion region, maximum width of the depletion. So that's how many charges are in the fixed depletion region, the acceptor ions, okay? In the maximum situation, in the onset of strong inversion. So now we have a way to calculate what the threshold voltage is. Okay? So going back here, this is the applied voltage. Okay? You have some voltage which drops across the oxide, some voltage which drops across the semiconductor. The voltage that drops across the semiconductor has to induce strong inversion, which is when a channel forms by our definition. That's a little bit arbitrary, right? We assume strong inversion, just that's an arbitrary setting. Clearly, there is some transition region. We'll talk about that later. But assume that strong inversion is the onset of the channel. Okay? That allows you now to tell what is the minimum voltage I should apply to the gate to create the channel. Okay? That's the threshold voltage. So now I can calculate the threshold voltage as essentially the voltage required to get the maximum depletion region, which is from here. Okay, QD divided by CI, CI being the oxide capacitance per unit area. Okay, and it's a negative sign because the charges are positive. Okay, and this is a p-type material. You have to apply a positive voltage on the gate. Okay, the QD in this case is negative, so this whole term becomes positive. Okay, 2 phi f we know is the band bending. Right? This is 2 phi f is the difference between that point and that point. So how much the band has to bend. Remember, phi f is just this distance. Okay? So the threshold voltage, in other words, is the potential that you apply needs to do 2 things. It needs to create the maximum depletion region beyond which the depletion region doesn't increase. and it needs to bend the bands to create strong inversion. So you need to accommodate for these two things. That gives you the minimum threshold voltage. Okay? That's the idea. So this is a very important parameter, and in a transistor design, again, device designers spend a lot of time trying to optimize this. This is, of course, an ideal case. In a real case, this is a little bit different, and we'll talk about that next. Okay? Which is, let's see. So my next one. Okay. Oops. Okay. So, as I said before, the threshold voltage is the smallest gate voltage required to reach strong inversion. It is the onset of the channel, and this is the point where the drain current will flow. So another way to think about this is if I plot the input voltage, the control voltage, Vg, is a function of the output, which is the current ID. In the case of the P channel, until I reach Pt, I expect zero current, so there's no channel. Right? So I expect nothing to happen until I hit here, and then something happens. This is, of course, a linear region. We'll talk about that. So that's the idea of the Vt. You need this much voltage to create strong inversion and account for the charges in the depletion region in the substrate. Okay? So that's the physical meaning of the threshold voltage. Now, of course, that also means, because now you have voltage-inducing charges, that means you have a capacitance. Like I said before, so that's your input capacitance, which is part of your input impedance, and you need to be able to count for it. Okay, so we have our familiar device, and the capacitance model is very straightforward. It's easy to understand too. Okay, so again, the device has an oxide here, an insulator, and you have a semiconductor. So the capacitance we are talking about is looking from the gate. So you expect some capacitance from the oxide, and you expect some capacitance from the insulator. And indeed, that's how you model it in a device. So you have a CI, which is the oxide capacitance, which we just talked about. And then you have a CD, which is depletion capacitance coming from the semiconductor. Okay, and they're connected in series, as expected. Okay, so it's easy to understand. The analogy is straightforward. Now, of course, when you have two capacitances in series, the equivalent capacitance is given by that, right? It's 1 over Ci plus 1 over Cd equals 1 over C. Okay, you should be familiar with this. So the Ci is something we know, which we just talked about. It's nothing but epsilon s divided by W. Now this is per unit area. W being the width, in this case, the width of the oxide. Okay, it should actually be D. Now, CD, the depletion capacitance, is voltage dependent. Very similar to the PN junction that we talked about before. So you have to do a differential. So CS, CD, which can also be thought of as with an S because it's a semiconductor, is dQ over dV. And the surface charge density is typically what's taken. Okay, so dQs over d phi s. Phi s being the surface potential at the interface between the metal and the semiconductor, oxide and the semiconductor. Okay, now we'll look at those in a bit more detail, but keep this picture in mind. Okay, so if you have a small signal that's applied to the gate, the capacitance it sees will be a series connection between an oxide capacitance and a depletion capacitance, which arises from the semiconductor. Yes?
So just real quick, so the DQ, that's area dependent, what you're saying?
Which one?
DQ off of CS, that's area dependent.
This one?
The smaller the area, the lower the DQ you have.
The charge density, yeah, this is charge per unit area. So we'll look at that in some detail now. But correct, yeah. If you have a, so remember, this whole thing extends out of the screen, right? So you have a third dimension here, which is the Z we talked about before. And we'll introduce that again. And that defines a cross-sectional area for the channel. So think about the channel essentially almost like a cylindrical. Okay, so if if you look at this in 3 dimensions, kind of looks like that. This is the length. This is the Z, the width or the depth. And this is the height of the channel. And the current flow in this case, that's drain, that's source current flow, and that's gate on the top. So keep that picture in mind also. Of course, this cross-sectional area will determine the charge, the total charges. Okay. Okay. So, if you, okay, there are 2 more things to keep in mind. Okay. Actually, so let me very quickly mention. So, the capacitance is a little bit different than what you're used to in a parallel plate. The reason being that the mechanism for the charge transport is very different than in a conventional parallel plate capacitor. Okay? In a parallel plate capacitor, when you apply a potential, you have metal, you apply a potential, let's say, right? And you switch the potential, so you have an AC voltage going through. The charges are sloshing back and forth, right, from the battery. Because the conductor, it doesn't matter, it's instantaneous almost, right? You don't really worry about the speed that the charge is transferred back and forth. In our case, we know, because we have a depletion region, that it is not instantaneous. You expect some delay. And that delay means that the frequency of the signal determines the capacitance to some extent. So if you have a low frequency signal that varies very slowly, you have a different capacitance than when you have a very fast varying signal. So you have a low frequency capacitance that's different from a high frequency capacitance. Okay, and that's a very important distinction, it turns out. Okay, and we'll come back and reiterate that in a little bit. So the most important, the simplest way to look at the capacitance, of course, is a function of voltage. Like I said, capacitance varies with voltage. Okay, and this is a very useful plot, which essentially plots capacitance as a function of the applied gate voltage. Okay, the reason this is useful is that you can actually measure this, and by measuring this capacitance voltage plot, you can extract important material parameters about the device, which is otherwise very difficult to actually extract. Okay, so it's important to understand. Now, and it also tells you the physics of what's happening to some extent. Okay, now this is again a P-type substrate, which means that the channel is N-type, and the applied gate voltage for proper operation has to be positive. Right, you attract the electrons to create the channel. Now, so let's start with the negative gate voltage. When you have negative gate voltage, we had accumulation last time. The physics was that when you apply negative gate voltage, you attract the holes. So you attract majority carriers. Okay, so they're always conducting. Right? So remember, then we lose control of the gate. So it's just like a resistor, essentially. Because it's always conducting, and it's a majority, because it's a majority carrier, they can respond really fast to changes in voltage, which means my dq over dv, which is capacitance, will be very high. Right? Capacitance is defined as how fast my charges respond for small changes in voltage. Right? That's my instantaneous capacitance. If this response is due to majority carriers, this number will be very high, which means they can respond really fast. The small changes in voltage can cause large changes in the majority carrier, because there are a lot of them. That's exactly what happens in accumulation. So if you look out here, when the voltage is negative, you have strong accumulation. The capacitance is very high. It almost basically reaches the CI. Okay? The reason being that CD is so high that you basically ignore it. Okay, remember? The total capacitance is 1 over C, is 1 over Ci plus 1 over CD. This is that. Okay, that's the series connection. If this thing is very large, I can basically ignore that. It goes away. Okay, and then the total capacitance essentially becomes insulator capacitance. It becomes constant, pretty much. In other words, the semiconductor really doesn't do anything because it's almost like a metal. It's almost like a parallel plate capacitor. Okay, so that's the picture to keep in mind. It's simple. Now, as you increase the voltage, of course, at some point you cross you start going down. Why? Because now you're starting to induce depletion. Okay? So as you apply a smaller and smaller negative voltage, or closer and closer to 0 volts, this starts pushing away the electron, pushing away the holes, start attracting electrons. As you push away the holes, you're exposing the acceptor ions. So you get positive charges. Sorry, negative charges. Okay, exposed, which are fixed. Now, of course, this number starts becoming smaller. Right? Why? Because you are now getting a slower reaction when you expose, when you create that depletion region. The depletion is much slower than accumulation because you're pushing away the majority carriers, as opposed to already having a lot of majority carriers and having small changes in them. Okay? So one is a little bit slower than the other. So this starts becoming smaller, which means that you have to take that into account. The whole thing starts coming down a little bit. Okay? So you have depletion, and at some point here, you have a situation which we will talk about, which is called flat band. Okay? What that means is that the bands are essentially flat on both sides. Okay? And that turns out also to be an important condition, important situation, which we'll talk about in the next couple of slides. Okay? That's the number 2 there. Then as you keep pushing, the depletion region increases, so you're pushing the holes away. Okay, the voltage is getting more and more positive, so you're repelling the holes. So you're exposing more of the acceptor ions. Okay, and the capacitance goes down because more and more the depletion region is contributing to the capacitance until inversion happens. Okay. When inversion happens, what happens is that locally you create negative electrons, right? You create a thin sheet of electrons which now act as majority carriers because the material becomes N-type, very close to the interface. Okay? When inversion happens, although you have a depletion region, but very close to the interface, you have majority carriers because it has become N-type. And there are electrons. So now, this capacitance starts going up again because you're getting contributions from the majority carriers, which can respond really fast. But now the majority carriers are electrons. Okay? So that's what's special about this. So this capacitance starts going up again. After some time, the depletion region really doesn't increase anymore like we just talked about. It reaches the maximum depletion, so nothing more happens to it. So the contribution to this term is very small from the depletion, and the only contribution comes from the channel of electrons, which are majority carriers, and then they can respond so fast that it becomes negligible again. Okay, so it reaches CI again up here. So that's the physics of what's happening. I want you to understand that picture, not just the math, because otherwise it will become very confusing. Okay, and you need to understand this for the p-type substrate very well, because the n-type substrate, this whole thing will be mirror imaged. I'll confuse you even more. Okay? So, but try to understand very clearly for the p-type. Okay? So again, the picture is very straightforward. So the model of the capacitance is very simple. So you have a CI in series with CD. Now CI is not voltage dependent. It's fixed. Okay? It's just like an oxide, right? It's just the thickness of the oxide determines that capacitance. In series with CD, which is voltage dependent, which depends on the depletion region and any majority carrier contribution. When you have strong accumulation, it's almost like a resistor. It's almost like a metal. Sorry. So it has no extra capacitance in the semiconductor, so just the CI. As you start getting depletion, this capacitance goes down to some minimum value and then goes up again as you get strong inversion. So keep that picture in mind. So and the equations are here. CI is epsilon S over W. W in this particular case, this is the width of the oxide layer, and this is the CS. Is the like I said, it's just the instantaneous change of charge versus voltage. The minimum value is important because that occurs when the maximum depletion width happens. Okay, so beyond that, the depletion width really does not increase, which is why the capacitance starts increasing. Okay? And then you can calculate. This, if you can measure it, it will allow you to calculate or experimentally determine what the acceptor concentration of the p-type substrate is, which is otherwise hard to do, as you can think about. Yes?
What's the relationship between CS and CD?
They are the same. Yeah. CS is more general in the sense that S stands for semiconductor, so capacitance of the semiconductor. D stands for depletion, CD. In most of the cases, the depletion region dominates as over here. But over here, the depletion region has very little contribution. So over here, it's called CS because it's mostly the inversion channel. So this number gets really large, essentially, and you ignore it in the total circuit, equivalent circuit. Okay, so that's a quantitative picture, okay? Now, again, also that's the ideal situation. Okay, we ignored a couple of things which we need to actually put back in, which are technologically important when you actually design an actual device. Most importantly, when you design a device for a certain threshold voltage and also a certain capacitance, you need to take into account a few other things which we have ignored. So let's put those back in. The first thing is very simple, which is the work function difference between the metal and the semiconductor. I don't know if you recall, when we started with the MOSFET, we assumed that the work function of the metal and the work function of the semiconductor was the same. Okay? In other words, this Fermi level to the top of the conduction band of this insulator, this Fermi level to the top of the conduction band of the insulator were the same. Of course, that's a simplistic assumption. It's not necessarily the same because you can have any metal, any semiconductor. Typically, by the way, in an actual device, this is really not a metal. In almost all the conventional integrated circuit MOSFETs, the gate is made out of very heavily doped polysilicon. Okay? Polysilicon means polycrystalline silicon. So remember, polycrystalline means you have lots of crystal domains. So it's no longer single crystal. It doesn't need to be because you're not using this with the energy bands. What you're interested in is you heavily dope it to make it look like a metal. Now, the reason you don't use metals is because metals are important impurities for silicon. So you cannot put gold there, for instance, because gold will diffuse into silicon and mess with its doping properties. So in most CMOS fabrication plants, you actually use a polysilicon substrate, a polysilicon gate with very heavily doped. So you put in enough dopant so that the conductivity is so high it's almost like a metal. Okay? So the work function here is typically some Fm, okay? But that will, phi m in this case, but that will be different than that for the doped silicon, okay? 5s. Which means that under equilibrium, I have to have some band bending. So this is the diagram under equilibrium. Before, under equilibrium, everything was flat because the Fermi level was flat and these two numbers are equal and the top everything was flat. But now we know for a real situation, they're not flat, they're not the same, which means that the Fermi level still has to be flat, there's no current flowing. So this whole thing has to bend down. So this is at equilibrium before you apply any voltage. Okay? In other words, there is a built-in voltage, built-in field, almost like a p-n junction. Okay? So what does that mean? So in this situation, the work function of the metal is smaller than the semiconductor. So you have a field which points this direction. The oxide has to bend this way. These bands have to bend down this way. Okay? Now, when this band bends down this way, you can see that the intrinsic level has gone down below the Fermi level. Okay? So here, of course, it's p-type. Now here it has become n-type, which means you accumulated electrons in that interface without applying any voltage. Okay? Which means if I use this device without applying any voltage, I will get a current. Okay? This device is normally on. I need to apply a voltage to turn it off. It's an important distinction. It's a normally on device. And it's undesirable for most situations, I'd say. But there are circuits where people actually use this. Okay? But typically, when you make the devices, this is what you get. So you have a problem. You have to solve it. We won't talk about how people actually deal with this in actual fabrication. Maybe if we have time in a few weeks. Okay, so of course, then you can define a flat band condition, because as you apply a voltage here, if you apply a positive voltage here, you pull this band up, right? This is your applied voltage, the Fermi level split. And you reach a situation where the bands become flat, okay? And that's called the flat band condition. And in this case, we can see the flat band condition is just a difference in the work functions. It's a difference in work function between the metal and the semiconductor, okay? Essentially, you pull that up, you reduce the band bending, and then you don't have accumulation anymore. Okay? Now you have reached our old equilibrium. So you can think of the flat band as the starting point of operation of a transistor. Okay? From there, you want to go further to get a threshold voltage, or go back, you'll get accumulation. So instead of being 0 volts before, now we have biased that to some flat band voltage. Okay? That's a real device. And we have to account for that. Of course, what does that affect? The most important thing that affects is the threshold voltage. So now you have shifted all the voltages up, which means the threshold voltage has to go more positive. You need to apply more voltage. You need to first get the flat band condition, then do more voltage to get inversion. Okay, so it's an important parameter to keep in mind. Okay, so the next thing that we ignore in a real device are interface charges. Now, as I said before, that in an oxide there are no charges because a perfect insulator cannot have any charges. But in a real oxide, you always have some charges, and you have to account for that. Okay, and how does that affect us? So let's look at the picture very qualitatively. So this is a very simplified picture. So you have metal, okay, or polysilicon, it doesn't matter, it's the same for our purposes. Then you have silicon dioxide. Okay. Typically you have some contamination like sodium ions, which is very common contamination in a CMOS process. Okay. So you have positive ions here, which are the so-called QM. So we have mobile ionic charges within the oxide. Okay. You can also have immobile fixed ionic charges, QOT, trapped charges within the oxide. And then at the interface between the oxide and the silicon, clearly you have to have something happening because you're going from silicon oxide to silicon. So you have some bonds which have to be rearranged and so on. So you expect some dangling bonds, essentially, some bonds which are not satisfied. Okay? Which of course means that you have electron charges. Essentially, you can have in crystal imperfections, you can have charges that are trapped, electrons that are trapped, or holes that are trapped, and so on and so forth. So you get charges which are typically positive in this particular case because this is a p-type material, and QF, you have oxide fixed charge. Okay? Then you can also have charges right at the interface, which are also called the interface trap charges. These are essentially, if you recall in our band diagram, if you had crystal defects, even though the band gap has no energy levels, if you have crystal imperfections, you can have some energy levels within the band gap. And that can trap charges, either impurities or electrons or holes. Doesn't matter. Okay? So you can account for all of that as trap charges. So all of these charges, of course, affect the bands. Okay? So, which is approximately shown here in the case of flat band. So some potential is applied here. Now this potential has to account for not just the work function difference, but also all these trapped charges, trapped and mobile charges. Okay? So in this example, the field is in that direction because there are so many charges which are trapped here. Okay? And in this case, the flat band condition is essentially the effective interface charge divided by, which you make an effective charge from all of these potential charges, and you divide that by the capacitance of the insulator. Okay? So typically, because that's a positive charge, a negative gate voltage is needed to reach the flat band condition. Okay? Now you have to account for both the real-world effects that we talked about. One is the metal semiconductor work function difference, and one is the interface charges. And you put those both in, you get an expression for the flat band voltage. which is phi ms minus qi over ci. Okay? So what does this mean? This means that the threshold voltage again has to be biased by this amount. You need to have extra voltage to take into account these situations. Okay? One important technological implication is that the 100 silicon surface has fewer interface charges compared to the 111. This we kind of remember, if you remember. The 100 has fewer atomic density in that direction versus the 111, so you expect fewer interface defects, which means that most MOS transistors, MOSFETs, are made on the 100 interface in this direction. 100 oxide polysilicon. And that's because you want to minimize that. Okay? These things, the problem with interface charges is that it's very hard to control them. So you want to minimize them first, because they can be kind of random. Of course, you don't want to have random fluctuations among billions of transistors in your CPU, right? Because it will be impossible to design. Okay? So that's the answer to so what, basically. Okay? Keep that picture in mind. Okay, so how does this affect threshold voltage, which is probably most important from our perspective? So our old threshold voltage only had two terms. Remember, we had this term here, QD minus QD over CI plus 2 phi f. We only had that term. But now we have to incorporate the flat band condition, which is this term. So you have 4 terms now for a real MOS structure for the threshold voltage. So you have phi ms minus qi over ci to reach the flat band. That's the work function difference between the metal and the semiconductor. This is the interface charges or any impurity charges. This is what we talked about before, the depletion, to account for the charges in the depletion region. And this is basically strong inversion, where you're pulling the band down from the p-type to the n-type. Okay? So these 4 terms will determine the threshold voltage of the transistor. This will tell me how much, okay, my gate, my input signal goes to the gate. Right? So let's say I have a small signal ready. This is my signal I'm sending to the gate to amplify function of time. Okay? Typically, the amplitude of this signal is small. You're trying to amplify, right? So it's small. This might be smaller than the threshold voltage. Right? So if I just send that in, nothing happens, right? I don't have a channel. Or the channel exists and I don't really get any modulation because it always exists. You have no control if it's an accumulation. So what I need to do is I need to bias the signal above the threshold. Okay? Instead of making that 0, I need to have some DC level on top of it. Right? I need to put some DC. And this DC must be, of course, it typically must be greater than the saturation voltage, but let's say it has to be greater than the threshold. That's why the threshold voltage is important. It is the minimum voltage required to turn on the transistor. And of course, you don't want that to be too high, right? Because if it's too high, that means in your integrated circuit, you'll need to have huge voltages, right? Because you have billions of transistors. You will have to apply huge voltage for every transistor, and the drop the class resistance. You can't have, you will need a huge power supply for your laptop. Right? You'll have to carry something giant around. It's not so good. So you want to, and of course you don't want it too low either. Right? If it's too low, it'll turn on spontaneously, right? If I have some noise or whatever, it'll just turn on. Then I have problems. I have power issues and so on. So this has to be designed very, very carefully. The threshold voltage is the first parameter that you're learning of the MOSFET and probably one of the most important ones. Okay? Now the sign. The sign of the threshold voltage is important. It's important because the p-type substrate and n-type substrate gives you 2 opposite signs, like I said before. It's easy to get confused, so you have to understand one really well and apply that same physics to the other, same logic. Okay? Now, and we'll look at that very, very briefly. But the idea for a p channel versus n channel is extremely important because in digital processing, the most common, most important, I would say, in terms of usage, most important operation in a digital circuit is the AND gate and the NAND gate. So for those of you who have taken digital logic, the NAND and the AND gates can basically do everything else. I don't know. I assume there is a digital logic class before this, right? Okay. So AND and NAND can be used to do almost all the digital logic operations. Okay? And the basic AND gate is essentially, and we won't do this class, but you should know this, is essentially connecting a PMOS transistor and an NMOS transistor in series. It's essentially an NAND gate, sorry. Okay? So essentially you take this transistor, okay, and you connect that in series with this transistor. So this N channel, this P channel. That gives you a NAND gate. This is physically how it's made. And you connect all these different things together, you can make digital logics. So what I'm trying to say is that it's very important to be able to do P and N on the same substrate. In fact, the ability to do this is what really enabled the integrated circuit revolution. We'll talk about this in the last chapter 9, I think. Okay? Which means that we need to understand both N and P. Okay? Quite important. The logic is the same, so it's not that difficult. You just have to make sure you're clear about it. Now, from the sign of the threshold voltage for the N and the P channel devices is you can break it into the 4 terms. So the N channel is shown first and the P channel is shown next. For the metal semiconductor work function difference, there's no difference. Okay, the work function of the metal and the semiconductor. There's a small difference because remember the substrate is lightly doped. So the Fermi level really doesn't change much. So the work function doesn't change too much. So that's always negative because it's polysilicon versus whatever substrate it is. The interface charges are typically also, this interface charge is usually positive, so with the negative sign it's usually negative. Okay? So these two things don't change, they are the same. But of course the depletion region for a p-type substrate is negatively charged. The acceptor ions accept the electrons, so it becomes negatively charged. But for an n-type substrate, it's positively charged, it gives away electrons, right? You have donors. So that's obvious from a p-n junction. So this is positive, that's negative. Okay, there's a negative sign there. And the same thing for the Fermi, the strong inversion condition. For an n channel, you're bringing it down. For a p channel, the opposite thing happens. You bring it up. Make it from n-type to p-type. In the case of the p channel, you're accumulating. Under inversion, you get holes at the interface. So keep that picture in mind. Okay? And clearly, if you look at these 4 terms, of course you want to control, like I said before, you want to control the threshold voltage very well. Okay? You don't want it to be too high, you don't want it to be too low. And if you look at this equation, what are the parameters that you can control? The only real parameter you can control, I mean, let's look at them. So the work functions you can't really control very much. There's only a few. You don't use metal, so you have polysilicon with some doping, and the Fermi level is pretty much fixed, okay, because it's very heavily doped. Now, on the other side, it has to be lightly doped, so you don't have much control either. So this is out of the question, pretty much. Okay, the interface charges, you don't have any control because they're random defects, essentially. You try to minimize them as best as you can. This one, you have control because it is a depletion charge. You can control that by doping. It's directly related to the doping. Okay. This also you can control because it's directly, these two are basically related to doping. Okay. So if you plot the threshold voltage, which is what you want to control, as a function of the doping concentration, because really that's all you have in your box of tricks. To make devices, you can change the doping. Okay, this is what you get. So for the P channel, you get, this is always negative, by the way, for the P channel, right? So this is negative, 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 negative. So threshold voltage is always negative for the P channel, which makes sense, right? Because you need to apply some negative voltage to attract the holes. P channel means you need to attract voltage. You need to apply more negative voltage to attract holes. So it logically makes sense. As you increase the doping concentration of acceptors for the P channel, for the, donors in this case, which is the N-type substrate, a P channel, this threshold voltage gets bigger. Okay. Of course, it is intuitive also, because as you increase the donor concentration, this number becomes more negative. Okay? There's more charges, more charge density. Okay? So it has to increase in the negative direction. So there's nothing special about it. What's more interesting is looking at the N channel. Okay? The P channel is very simple, logically straightforward. N channel is much more interesting if you think about it. Okay? When the doping is very low, which is, by the way, most of the time, because you want to have a lightly doped substrate. You don't want it to be very heavily doped. Why, by the way? Yes?
So it switches faster?
No, you want it to be lightly doped. The switching, well, it's partly correct, yes.
I would imagine that means a smaller change in the field on the gate will produce more depletion.
Yes, and they're both correct, both are related. So what you're saying is that, remember, when the substrate, the depletion region is almost entirely in the substrate, right? And the reason that is the case is because the substrate is lightly doped. Okay? If you heavily dope it, then the impact of the depletion region goes down, and then the control from your gate goes down, in a sense. Okay? You have to think about that effect, how the gate is controlling that channel. Okay? So, but let me ask you, look at this curve, because this is interesting. If you look down here, which is lightly doped P-type substrate, okay, N channel, your threshold voltage is negative, which means if I don't apply any voltage, or if I apply 0 volts, I still have a channel. Okay, this is what I said before. You have a normally on device. So if I apply 0 volts, I had a situation like this, where I don't have a bias. I have a channel, but I am in the linear portion of the channel, so I don't get any amplification. Okay? And I can never turn it off. So I cannot switch it off. So that's problematic, like I said before. Okay? Of course, you can overcome it by applying more, so which means you just shift your threshold voltage, right? So you have to apply higher voltage. So as you increase the doping in the case of the P-type substrate N-channel device, the VT increases. At some point it becomes 0, which is what we expect, which is the conventional case if we did not have these first two terms. Okay? And then as you keep increasing, you get higher voltage. Of course, this increase comes from the fact that this number is positive here and QD is increasing. Okay? You just have higher concentration of, in this case, of acceptor ions, P-type substrate. Okay, so VT less than 0 here means that the channel is present before applying a voltage. The normally on device, also called a depletion mode device. How is the device turned off? Of course, you can invert it, right? Just apply higher voltage. You apply, in this case, N channel, right? If you want to turn it off, you apply a negative voltage, right? You go towards accumulation. Is that obvious? Okay, think about that a second. Here, if I apply 0 volts, I already have an interface charge. I have, electrons sitting close to that interface, forming a channel. If I want to turn off that channel, I need to push those electrons away. So apply negative voltage. Repel those electrons away. Get rid of the channel. Then it turns off. Which means that I need to go below the threshold voltage in the opposite direction, more negative, turn off that device, which is problematic also, right? Because I need a huge dynamic range in my voltage. It means I need to go to very negative voltage, and if I want to make it work in saturation, I need to go very, very positive voltage, which is very difficult to do in a negative device. You don't want that. So you want to deal with this on the device level. Typically, they play with device design characteristics to avoid that, which we won't really talk about. Okay. So again, to remind you, the two types of devices essentially look like this. This is what you have not seen, or typically haven't looked at carefully. The N-type substrate, you have P plus typically here, P plus typically here. You have metal oxide. And in this case, of course, the electrons are the majority carriers. You apply a negative voltage. Okay, you push the electrons away. You make a depletion region. And you apply more negative voltage. You pull the holes closer together to this interface. You create a P channel as opposed to an N channel before. So the logic is exactly the same, but the signs are all inverted. Okay, in this case, you have to apply a negative voltage as opposed to a positive gate voltage. So as long as you understand the logic of the P-type substrate device, you'll be able to follow the N-type substrate device as well. Okay, but make sure you're very clear on what's happening. And you have to be very careful with the signs when you actually do the calculations. Okay. For the N-type device, which we have seen, we're very familiar with this now. You have P-type substrate, and you have an N plus region. You apply a gate voltage, you apply a positive voltage, you push away the holes, you create depletion, you put enough positive voltage, you attract electrons, create an electron channel, N channel. Okay? So positive voltage creates an N channel, negative voltage for the other type creates a P channel. Signs are reversed. From the drain to source perspective, there is no reversal of sign. So now we are only talking about the gate control, right? But the input-output voltage, they are the same. Current flows from drain to source. In the previous one also, current flows from drain to source. It's just drawn the other way, but it's exactly the same, right? I can draw it the other way. Okay. So there is no sign reversal for the input-output characteristics, but there is a sign reversal for the transfer characteristics, which we will talk about. Yes?
There's no physical difference between drain and source, right?
That's correct. It's symmetric. It's purely symmetric. In fact, we will look at how they are fabricated. No physical difference.
So even if you messed up and did source to drain, you really wouldn't be messing up and doing source to drain. You'd be doing drain to source, right?
That's correct. Except that when you start connecting them in circuits, you cannot mess that up.
Well, yeah.
Because you have to have a common ground voltage.
Right.
But otherwise, you're right. Typically, remember, the source is usually connected to the gate. Source is usually connected to the body, which is this substrate, and grounded. Okay? These two things are usually connected together, the source and the body, and they're grounded. The body is typically just the silicon wafer, the wafer that's fabricated on. And that's the ground terminal, typically. The whole thing is grounded. Okay? And that in your digital logic, your ground line, that's basically it. Okay, so let's look more carefully at the capacitance analysis. Now, with the real world knowledge now, okay, what we know. And the reason to do this, like I said before, is because you can measure this. So you can apply a voltage, okay, and you can measure how capacitance changes. You take an oscilloscope and you can measure capacitance, right? And so you can get this curve. C versus voltage very easily. And it turns out from this curve you can extract a lot of the more difficult to extract parameters of the device, like doping and so on. Okay, we'll show that. First of all, like I said before, there are two curves, one for high frequency and low frequency, and this has to do with how the charges respond. So the high frequency curve, the low frequency curve is what we saw before. You have at under accumulation, it's very high, it goes down. This is what we saw before, and under inversion goes up again. High frequency is different. We'll talk about that in a second. Let's just revisit what this capacitance voltage curve physically means. Okay, out here, this is again N-channel device, P-type substrate. Gate voltage is positive. Okay, so when the gate under normal operation, when the gate voltage is negative, it is in accumulation, right? You basically attracted all the electrons. When the gate voltage is negative, you attracted all the holes. So majority carriers are basically attracted and forming a channel, and you have no control, essentially. Okay? You really have no control on the gate, which means that the capacitance is essentially from the oxide. Okay? And it's the peak, as high as it will go. Now, as you increase the voltage, you start depleting the channel. Okay? You start pushing away the holes, and you start exposing the acceptor ions. When you do this, because they're immobile, the capacitance from the depletion region starts to come into play into this equation. Okay? So you need to take this into account, and the total capacitance comes down to reaches a minimum when the depletion width is a maximum, and that's when this number is the smallest. Okay? So this inversion is the largest, and you need to take that into account. Okay? After that, strong inversion comes in, and then it becomes N-type, and the majority carriers contribute, and the capacitance goes up. This term goes down, essentially. This whole term basically gets ignored, and the capacitance goes up to the oxide capacitance again. So that's relatively straightforward to understand. This is low frequency. Slow signal. If you have high frequency, so let's just reiterate, go through this. So first of all, if you look at this plot, the low frequency plot, this can tell us if the substrate is P or N-type. First of all, you will see that this plot is not symmetric across 0 volts. Okay? Or you can just do the low frequency, high frequency plot, and we'll see what the high frequency is, why is it different. You can see the difference here. At the positive voltage means that this is a P-type substrate. For an N-type substrate, this whole thing will be mirror imaged. In other words, accumulation happens under positive voltage, and inversion happens under negative voltage. So just by looking at this plot, you can say whether it's a PMOS or an NMOS transistor. Okay? That by itself is useful, because you can't tell by looking at it. Okay? That's the first thing. Second, if you look at the high frequency and the low frequency, first of all, the definition of high and low frequency has to do with how fast is the signal relative to the recombination generation rate of minority carriers. That's basically what that means. And the reason for that is the depletion region creation has to do with pushing away the majority carriers, but the inversion channel is created by minority carriers in the bulk. They have to be generated. Right? And you also need to account for recombination as they're diffusing. Okay, so the signal is fast compared to when the generation can happen. Then this contribution will be just from the depletion and less from the inversion layer. Okay? You think about that. The reason this goes up is because the inversion channel that has been formed, which basically the majority carriers right at that interface, they can respond really fast. But they need to form first. They need to come from somewhere. Right? They need to diffuse from the bulk to the interface. That takes some time. So if you have very fast varying signal, the charges don't have time to reach there, which means that they don't really contribute to capacitance. And the only contribution to capacitance in that case comes from the depletion region itself, and it's essentially flattens out. And that value is essentially 1 over Ci. This is fixed, independent of voltage, plus 1 over Cd. But this Cd is now the contribution of capacitance from the maximum depletion rate. It's a little bit different from the low frequency, which has to do, we'll ignore that for the time being. Just ignore that difference for now. That has to do with the interface trap charges. Right? Less important for our discussion. But the physics, you have to remember, there are two things happening. One is you're revealing the fixed ions. In this case, the acceptor ions. Okay? And that can happen relatively fast because you're pushing the majority carriers away. But not as fast as just majority carriers changing their concentration. So it's slower than accumulation, but faster than, slower than accumulation. This is the only comparison now. Okay? But when you have fast charges, you need to account for the fact that the interface channel cannot be formed unless minority carriers are formed in the bulk and they diffuse to the interface. So that takes some time. for the inversion channel to form. Okay? That accounts for the difference between the high frequency and low frequency. And of course, again from this plot, you can tell whether it's p-type or n-type. Here in accumulation, the majority carriers respond really fast, so there is no contribution from them pretty much. Okay, and this decrease shows depletion, as we saw. And the oxide capacitance we saw before is epsilon I, the permittivity of the oxide divided by the thickness of the oxide, which will become very important shortly. The minimum capacitance, again, the capacitances are connected in series. The minimum capacitance, as I said before, is Ci and CD min, this is when the depletion region is maximum. Okay? The capacitance is minimum and the thickness is maximum, right? Remember, it goes as 1 over the thickness. And by knowing the minimum capacitance, and we know this number, okay, because we know that number, we just measured that. And by knowing this minimum, we can calculate that. And by knowing that, we know the maximum depletion width. As we'll see shortly, from the maximum depletion width, we can extract what the substrate doping is, which is, again, an important parameter, difficult to measure typically. Okay? Now, we'll go back and talk about it in a second. But around here somewhere, flat band condition happens. And in that case, you get capacitance, which is from the depletion region, which is referred to as a Debye capacitance, which has to do with the screening Debye length. But again, less important for our conditions. But by looking at this flat band condition, we can calculate what the flat band voltage would be. Okay? So what we are able to do from this plot is essentially the following. We are able to estimate the terms that go into the threshold voltage. So we can experimentally determine what the threshold voltage is without even having to actually run the capacitor. Run the MOSFET as a device. Okay? Because this first two terms gives us the flat band condition. Okay? And the last two terms can be calculated from the doping concentration. Because QD is just the depletion charges. Phi F, remember, is just the difference between the intrinsic level and the Fermi level. Again, comes from the doping. Okay? So by measuring this capacitance voltage curve, we can actually determine experimentally what the threshold voltage is. Okay? Very important parameter of the MOSFET. Okay. Now, there's another advantage, by the way, to the capacitance curve. The advantage is that you don't actually have to wire anything up. Right? You can have a device which is not connected to anything here. Just apply a voltage here. With respect to the body, right? You apply an AC signal. So it's a much simpler experiment also to do. To stick an oscilloscope, right? So it's much simpler to measure as well. Now, one other characteristic that we ignored, we have to introduce as well. Now, so far, before I go into that, so far we only talked about the capacitance across the MOS, the Metal-Oxide-Semiconductor Interface. But it turns out, although the oxide is an insulator, if the oxide is thin enough, you can have a current going through. You can have a current voltage characteristics of a metal-oxide semiconductor interface as well. Okay? This is, of course, undesirable. You don't want that current to flow, but it happens. And it's very, very important for the most advanced devices, as I'll show you. But first of all, even for conventional devices, you can have a situation. This is the energy band diagram. So you have a polysilicon gate, let's say. Okay, Fermi level, valence band is here, conduction band is here. That's pretty much the Fermi level because it's heavily doped. So heavily doped means the Fermi level is almost right at the conduction band, pretty much, right? Now, and then you have some electric field on the oxide, and then you have on this side silicon. If this electric field is large enough, and we saw this before, the bands can bend so much that the electrons which are sitting on this side can tunnel across into the conduction band of the oxide. Okay? If that happens, then it can very easily just hop down to the conduction band of the silicon because it's lower in energy. Which means that if you apply enough of a voltage, you can have a current flowing this way through the oxide. It should be impossible because they're insulated, but it can happen if it's thin enough and you apply high enough voltage. Okay, and this idea is called the Fowler no-time tunneling, and you don't need to understand how it's derived, but it's a quantum mechanical tunneling, very similar to what we talked about before, and it's proportional to two things. First, it's proportional to the oxide electric field, which is obvious, right? Because the more the electric field, the more it bends, and it becomes easier for the electron to tunnel through. This also depends upon this energy barrier height, inversely dependent upon, inverse exponential. Okay, so that's a little bit common sense. So, but more importantly, in the most advanced devices where you scale down the devices, you made the devices very small. Remember last time we talked about 40 nanometers. And today in the research, people make transistors which are about 9 to 10 nanometers long. When I say long, I mean this. They're very, very small. And it turns out, when you scale things in this direction, we'll talk about this more in chapter 9, you need to scale things in this direction as well. Otherwise, you end up with big fringing fields and so on. So you have problems in your current characteristics. Which means that the oxide thickness has to be extremely thin. So an example is shown here. Okay? So this is a transmission electron micrograph of an advanced transistor, where of course you have a silicon substrate. This is our body. Okay, channel is formed right there, and you have an oxide. And look at that, 1.2 nanometers. That's about 10 to 20 atoms of silicon. Pretty small. Okay, and then you have polysilicon. In fact, if you look carefully, you can see the atomic electronic wave functions actually. Okay? So it's pretty incredible that you can actually see it. Now, when this becomes really thin, if you look at the energy band diagram, this barrier now becomes very thin. So electrons can tunnel through, basically have direct tunneling, which means that from the top of the conduction band, it can tunnel right across into the semiconductor. Okay? And this is a problem. This is a problem because this, first of all, is an undecided current. Okay? So you expect some problems with the current voltage characteristics in the input and output. We won't talk about right now. But you can, using common sense, we can imagine that if this current flows at very low voltages, that is an energy loss, right? You're just passing current through some resistor, you're creating heat. That turns out to be a big problem. So imagine you have billions of transistors, and each transistor has a little bit of so-called leakage current, and loses heat. Okay, and you add them by billions of transistors, you get a pretty significant heat loss, which is the reason why your big computers have to have a fan. One of the main reasons, by the way, and the reason that computers get hot. You're losing heat because of this so-called leakage current. And this can happen even when you apply no voltage or very low voltage to the gate. Okay? To avoid this today, which you should be aware of, people use what are called high K dielectrics. So essentially they try to increase the permittivity of the dielectric material. So instead of just using oxide, they use a fancier material called hafnium oxide, which has an epsilon which is larger than silicon oxide, which means that you can maintain the same capacitance, which turns out to be important. Okay, remember, capacitance goes with epsilon over D, by making D a little bit larger. So there's an example shown here. So you have a gate, 1.2 nanometer oxide, and the silicon substrate. So okay, this is the 90 nanometer CMOS process. Okay, this is probably 2 or 3 years old now. Nowadays, it's like 32 nanometers, so you can get a sense of progression. And that 90 nanometer, by the way, approximately relates to the length of the channel. So we'll talk more about it in chapter 9. But anyway, if you look at the capacitance is 1x, let's say, so relative capacitance. Leakage current is 1x. But if you replace that with hafnium oxide, which is a higher dielectric, so you can use a thicker layer, 3 nanometers, twice as thick, roughly. What happens? You can see the capacitance is now increased to 1.6x, which is a good thing, as we'll see. You want a high capacitance, a high impedance going into the small signal. At the same time, the leakage current is now 100 times lower. And the reason for that 100-time decrease is a thicker oxide. So remember, this tunneling current depends inversely, exponentially inversely on the thickness. Okay? We go back and think about what we talked about, the quantum wells. Or the particle in a box with a finite energy level. Okay, so that's a very important technological advancement, which, by the way, has really driven Moore's law. Without this, it wouldn't really happen. Okay, so let's see. I think let me see what's next. I forgot. Okay, we'll stop here, and then next class we'll talk about the other side. So let me, before I forget, keep the picture in mind. We have only talked about the metal-oxide-semiconductor part of it. Okay, we have only looked this way. But in reality, the transistors are used this way, right? The current flows this way. We saw that for the JFETs and so on. And that's what we'll talk about next. Okay? Okay, see you on Thursday. Oh, I have your thing.
Thank you so much.
Sure. TJ Duke, you're here. Okay. Brandon Cross. No? Brandon's not here? About what? Yes.